So today, I think if I'm able to go quickly enough, we can finish introducing all of the new content on limits and continuity, but there's going to be a lot of exercises to do afterwards, so we won't be done with Chapter 2 per se. So the roadmap is I have a couple short limit questions, some Epsilondelta stuff to warm up. Then we're going to practice the definition of limits by defining a couple related notions, slight modifications of the old limiting definition, which will require you to remember the Epsilondelta definition and change it slightly. Then there's this important theorem. I think this is the first thing that we're proving in calculus, which actually gets the name of theorem rather than just a proposition. The squeeze theorem will be useful to compute limits where it's challenging to use Epsilondelta directly. This lets us do kind of a trick. Then I want to take a quick interlude about halfway through to just preview the rest of the course, like since we're doing calculus proper now, to give just a context and a big picture, I guess, view of where we're going. And then we'll do the continuity stuff, which is the main deal. And if we have time, we can get to this important result that all polynomials are continuous, which we'll see that the statement basically means that they behave as you saw when we took things like the limit as x goes to 2 of x squared. Remember, we computed this and it was 4. So you might think, oh, polynomials seem to have this nice property that the limit is always what you get by just taking this value and plugging it in. Obviously that's not true for all functions, like stars over Babylon does not have that property, but you might think it's true for polynomials, and in fact we will see that is true and we'll prove it. So thoughts or questions on the plan?
I don't have any thoughts or questions.
Okay. Alright, here's a warm-up. This is taken directly from the AP Calculus exam. So it shows us two functions. Here's g on the right, which has this kind of point moved. So at x equals 1, it looks like g gets close to 2, but the actual value is 1. And then there's this other function f on the left. So they ask us to find, no proof because it's multiple choice, just find what is the value of the limit as x goes to 1 of f of g of x. So this is composed, f of g of x. So that should take maybe about 10 seconds to figure out.
Okay, is this... No, this is just 2.
2. Can you walk me through how you got to 2?
Okay, it seems like we're just finding... Wait. So can we simply insert 1 into the g of x?
Insert 1 into g. If you insert...
No, I don't know. No.
Yeah, so it's definitely the case that g of 1...
So it would be C, 3.
3, okay. So how did you walk me through how you got to 3 then?
So the limit of g of x as it approaches 1 would be 2. And you take the 2 and you place it into the former function f and you get a 3.
Good, okay. So this is correct. They're checking here that you understand that limits commute with basically this, I don't know if commute's the right word, but limits behave as you'd expect with function composition. So if you compose these functions, since the inner function gets close to 2, and the value of the outer function at 2 is 3, it is indeed the case that their composite approaches 3. Good. We haven't actually proved that, but I want to intersperse some AP calculus questions just for context, and they don't really ask you to prove anything, so that's a hedge. But okay, good. So another warm-up question. First, I will prime your brain for the question by reminding you of this function we studied a while back. So we looked at this ratio of x squared minus 1 over x minus 1, and we saw that you can compute the limit by factoring the top as x plus 1, x minus 1, and then you notice that when x is not equal to 1, that's the same as the function x plus 1. So the graph looks just like a line with a point removed. But as we know, the limit is insensitive to what actually happens at the value in question. So since the line, even though it's missing that point, since it gets closer to 2 at 1, we argued that the limit is 2. And you can prove that by just let epsilon be given, take delta equals epsilon. So the takeaway from this example is that often we can compute limits doing these sort of algebraic tricks by manipulating a numerator or denominator or doing something to make the expression look more obviously like a recognizable function. Good.
Is your saying algebraic gymnastics here a reference to me saying code parkour?
No, algebraic gymnastics is a term that I have used for a few years now, but I do like the term code parkour very much.
Just making sure.
Good. Algebraic parkour, perhaps, if you will. Okay, so here's a related problem. So now I will ask you what I should do to compute this limit. The limit as x goes to 1 of x cubed minus 1 over x minus 1. And your hint is the difference of cubes formula. So what should I write to compute this limit? What should I do in this next step after this equals sign?
It seems like we... Wait, nope. Can we just write this as a piecewise function? Or no, not quite yet.
We could write it as piecewise because it's basically going to be something simple when x is not 1, and then undefined when x equals 1. But to do that piecewise thing, we have to figure out what is the simpler thing it equals when x is not 1. So what algebraic gymnastics, like in the previous slide we factored the top, what should I do here to express the top in terms of other quantities?
Are you suggesting that we assign a value to the numerator?
No, I'm suggesting you factor the numerator. I'm saying using difference of
Oh
cubes.
boy!
Yeah. So what should I write in the numerator?
So I believe that you can write x, okay, x minus 1 times x plus 1, and
No,
I don't know if that...
you gotta use this formula, the difference of
Yeah,
cubes.
yep.
So
Okay, so that would be x minus 1 times... yes, no, is it... This is gonna be me... What? Soap. Yes.
soap.
Same, opposite, always positive. So this is going to be, and then x squared plus, no, x squared plus negative x. That's the second time I accidentally said plus negative, but you can just say minus x.
I think it should be x squared plus x plus 1.
Right.
Right. So if you use the formula up here, this is the same thing with a equals 1. So this is minus, if you move this minus inside, this first thing gives you x minus 1. And then when a equals 1, this thing is x squared plus 1 times x plus 1. Right?
Oh, right, because the difference of cubes is you ignore the minus sign in getting the quote unquote. In this case, it would be a.
Yeah, because the word difference in difference of cubes already takes care of the minus sign, right? So, right. Okay, so let's do that. And then this is where the magic happens, because we know that the limit is insensitive to the value at x equals 1, so we can assume that x is not equal to 1 and simplify this expression, which means that we can cancel top and bottom, right? So this again is not true. In general, the function is not always equal to this quadratic part, x squared plus x plus 1, but it's true for the limit, since that ignores the value at 1. And again, we haven't proven this with epsilons and deltas, but you might believe that for polynomials, the value of a limit is always what you get by plugging in to the corresponding expression. So if we assume for the moment that that's actually true, what is the value of this limit then?
Value of this limit would be 3.
3. Good. Okay. Good. So it seems like you're okay with the algebraic gymnastics. So all this just looks like a parabola with a hole in it, right? So this is a parabola which would hit the value 3 at x equals 1, but we've just put a hole there. And yeah, you might wonder why we have all of we're considering so many functions that have points removed or holes missing, but we'll see when we use limits to compute derivatives that a derivative is exactly this form. It's something that it has a denominator. There's a difference in the denominator, which means the function is formally not defined when the denominator is 0. So we'll take limits to get around that. Okay, good. All right. Now to make sure that you have this definition deep in your bones, the Epsilondelta definition, I've just put like Mad Libs here. So I'll ask you, what are the things that go in these blanks in the Epsilondelta definition of a limit? So the first one, I guess, we say that the limit as x goes to a of f of x equals L if for any, what comes first?
I believe that you can put down in there f of x.
In this blank?
Yes.
I think, let's get a picture of the rest of it. So for any this, there exists a something else such that whenever something is true, something else is true. So I don't think putting f of x would help here, because for any f of x is a little strange because we've already kind of used the term f of x here. So I don't think f of x is the right piece. Right? I think this is for any epsilon greater than 0, right? Okay. So we say that the limit as x goes to a of f of x equals L if for any epsilon greater than 0 there exists a what? What goes here?
Delta greater than 0.
Good. There exists a delta greater than 0. Now the
I had no idea that this. I kind of was keeping limits and epsilon delta separate in my mind just a few seconds ago.
Oh, well, you shouldn't keep them separate because the epsilon delta is the definition of the limit, right?
Yes.
Good. So they should be as unseparate as possible. Good. Okay. So there exists a delta greater than 0 such that whenever what goes here? This is the blank that's about our input tolerance, right? So what inequality do we write to express the input tolerance? Well, it should be an inequality involving x, right? This is the inequality that tells us x is within a distance delta of a, but not equal to a. So how do I write that mathematically?
This is a total guess. I believe that you can put down the absolute value of x minus epsilon.
Well, we want x to be close to a, so it should be absolute value of x minus a.
Oh boy, I'm doing terribly.
Okay, so if x is supposed to be within a distance delta of a, what inequality do I write?
That there is greater than 0.
Well, it's certainly greater than 0, but it has to be less than delta, right? Good. So this is the statement that x is within a distance delta of a, but not equal to a. Okay, what inequality do I write for this output tolerance? What goes here? There's some inequality.
I believe that this is 0 is less than the absolute value. Well, I don't know if the 0 is necessary. You've omitted that before. That value of f of x minus a.
Well, f of x goes to L, so this should be capital L here. Right. Good. Less than epsilon. Okay, now I will ask you to read this completed definition out loud to cement it into your brain, so go.
We say that the limit of f of x as x approaches a equals L if for any epsilon greater than 0 there exists a delta greater than 0, such that whenever 0 is less than the absolute value of x minus a, then delta, it is also true that the absolute value of f of x minus L is less than epsilon.
Good, okay. As Spivak said, if you have to memorize it like a poem, because otherwise all of your proofs will be wrong. Good. Okay, so here, this is the old kind of fundamental definition of a limit we did last time. So now we're going to try some modifications. So one of them is limits at infinity, and this is, I think, the intuition for the limits you gave in the consolidation document, and it's also more closely related to the definition of E and the computation of pi that we did before. So our previous definition, the Epsilondelta one on this previous slide, only tells you how to define a limit at some finite point A. So we need a new definition to discuss whether a function has a limit at infinity. So for instance, if this is the function 1 over x, we'd like it to be true that the limit as x goes to infinity of, say, 1 over x equals 0, right? We'd like to be able to make statements like this, but we haven't defined this symbol, x goes to infinity. So kind of, I guess this is part of the fun of mathematics, is thinking about the right way to phrase your definition to get the properties you want. So roughly we want the property that we want this to imply that you can make this function 1 over x as close to 0 as you'd like by making x large enough, right? By making x kind of closer to infinity in some sense. So I'll ask you, I've written part of this definition. We say that the limit as x goes to infinity of f of x equals L. And I'll ask you to kind of modify the epsilon delta stuff from the previous slide to make a definition for this limit at infinity. So what do you think should go in the first blank, for instance?
So this is going to be worded similar, just substituting a for infinity. So we can start with for any epsilon greater than 0.
Okay.
There exists delta greater than 0.
Delta greater than 0. Okay.
Such that 0 is less than the absolute value of, I want to say x minus infinity.
Can't do that. You can't. Infinity is not a number. This is the part you have to change. So what is the generalization? I'll show you the previous slide again. So here, that slide was, or that line, that 0 is less than x minus a is less than delta. This is telling us that x is close to a. So our input tolerance is measuring how far we are from a. So what is the generalization if we want this to get close to 0 as x gets bigger? What should go in this blank, which is now the new idea for when x is big enough rather than close enough to a?
Could it simply be the absolute value of x?
Absolute value of x, what? That's not a statement.
Is less than delta?
Such that...
That's the total guess.
Well, let's think about what this statement means. So, absolute value of x less than delta means x is close to 0, right? This is saying x is within a distance delta of 0. We're trying to define a statement that says when x gets very large, the function approaches some number L. So what can we use to express the idea that x is sufficiently large, x is large enough?
Perhaps x minus L?
Well, we shouldn't combine x and L. L is the value that the function approaches, not what x approaches.
Don't know.
So let's create a statement which says x is sufficiently large. X is larger than some bound. I think think it might also help if we use a different letter, because I think of delta as a small quantity, right? Lowercase delta is like a small number. So maybe we should call this like a capital delta. So capital delta is some big thing, right? So if I want to prove that the limit as x goes to infinity exists, I need to prove that to make this function close to L, I can take x large enough. So maybe to make 1 over x smaller than epsilon equals, I don't know, 1/100th, to make this thing smaller than 1/100th, you would ask the question, how big do I need to make x? And then you would say, okay, that's fine, then I just need delta to be 100. Because then when x is bigger than delta, when x is bigger than 100, this function 1 over x is smaller than epsilon, which is 1/100th. Right? We're creating a definition so that when x is larger than some lower bound, the function is sufficiently close to the target value L. So I think what we want in this line is when sorry, did you say something?
I'm gonna guess you would place down the absolute value of x minus delta, but I don't know what other inequalities would go with that.
I think we just want x bigger than delta, right?
Oh, well,
Right, we're trying to define a limit as x goes to infinity, right? So this is supposed to be when x is larger than something.
oh god, my Discord just broke.
Did you stop screen sharing again?
There we go. It just fixed itself.
Good. Okay, so this is the definition of a limit at infinity. So we say that the limit as x goes to infinity of f of x equals L if for any epsilon greater than 0, same thing, any output tolerance, there exists a capital delta greater than 0. So this is no longer an input tolerance. This is how far to the right do you have to go? How big do you have to make x? There exists a capital delta greater than 0 such that whenever x is bigger than capital delta, then you will be within epsilon of your output tolerance. Absolute value of f of x minus L is less than epsilon. So this is saying as x gets big, this thing gets close to L. Right? Okay, ask me questions on this, because I feel like this isn't totally clear. Or did your Discord break?
I'm still here. I don't see any questions to ask.
Okay, I'll ask you a question then. So we don't have to write it out, but how would you define the limit as x goes to negative infinity? So what would the definition of limit as x goes to negative infinity of f of x equals L be? Which part of this needs to be modified if we want a function to approach some value at minus infinity?
I believe we would substitute, well, swap delta is greater than 0 for delta is less than 0.
Good, so delta would be negative, and then what would this condition become? Since now we're... oh, sorry.
This would become x is less than delta.
Good, yeah. Okay, so yeah, to get a limit at negative infinity, you're saying there's now some number such that if x is further to the left, if x is less than that negative number delta, then you will be sufficiently close to your target of L. Good. Okay, yeah, those are limits at infinity. All right. One other notion of limit which we will need is one-sided limits. So when we spoke about these piecewise defined functions that have a jump, right? This, for instance, thing that stays at 1 for negative values of x, then jumps up to 1 for positive values. So the limit does not exist here because if you choose epsilon bars of, I don't know, like a half around either of these values, you can see that you're going to have some values near 0 that give you a 1 and some that give you a 2. So you can't guarantee that all the values will lie within these epsilon bars of a half around either number. So the limit does not exist at 0. But nonetheless, sometimes we'd like to discuss the behavior of functions like this from just one side, just from the right or just from the left. So for instance, we'll define the one-sided limit from the right, which will be written like this: the limit as x goes to 0 with a superscript plus. That means it goes to 0 from above. We'll make a definition so that that is 2, since this thing gets close to 2 as you approach from the right. And we'll have a second definition: the limit as x goes to 0 superscript minus, which means from the left. The limit as you approach 0 from the left is 1. So the point is that even when the ordinary limit does not exist, sometimes you can still have existent left and right limits. Okay. Is that idea okay?
Yeah, I'm seeing this in my strange zooming analogy as splitting the screen vertically.
Ah, yes, good. Yeah, so you split the screen vertically and you can zoom in on one of the two split sides, then the one-sided limit exists. Good. Alright, to practice more with the definition, I will ask you to define the left and right one-sided limits. So it's going to be the same thing. There's going to be an Epsilondelta definition, but one piece will be modified. So let's say we'll do the one approaching from the left. So we say the limit as x goes to a from the left of f of x equals L if for any what?
I would believe that in here we would insert epsilon is less than 0.
Epsilon less than 0. Epsilon is still the tolerance of the function from L, right? So I think epsilon still has to be positive, right?
Oh, wait. Yeah, I butchered that.
Good. Epsilon greater than 0, there exists what?
I believe since we are coming from... Okay. So I don't know if we're always interested in limits at 0, so...
This could be any a, not always 0. So
yeah.
So I think we still want this to be a delta greater than 0. This part won't change, but the thing that we say here to describe x being within a distance delta of a, this will change, right? So this line, which was before it was 0 is less than absolute value of x minus a, is less than delta. Now we want to change that condition so that x has to be on the left side of a, right? We still want it to be within distance delta, but it has to be on the left side. So what should I put on that line then?
So I believe that we are going to put down 0 is less than, and this time around there's going to be no absolute value sign.
Right. Okay.
So minus a is less than delta.
0 is less than x minus a is less than delta. Okay, so this means, wait, I think we want, if this is coming from the left, then x is going to be smaller than a, which means x minus a is a negative number. So I think, shouldn't this one be a minus x? It's less than delta. Is this right? Because I think if this is a, and we want x to be approaching from the left, right, then the distance between x and a is going to be a minus x, right?
Yeah, I see what's going on.
Okay. And then this piece should be, I think, unchanged. F of x minus L is less than epsilon. Okay. Good. Yeah, so this gives us the limit from the left. And now how will the limit on the right be different? So I guess the only interesting piece is that left line. We still want any epsilon greater than 0. There is a delta greater than 0. And now what do I put here?
So here we would place down 0 is less than, and once again omit the absolute value. X minus a is less than delta.
Yeah, good. And then this will be that f is within epsilon of L. Good, okay. So now we have left and right one-sided limits, and maybe I'll make this a daily challenge when you get back. As an exercise, you can show that if the left and right-sided limits both exist and they agree, then the ordinary limit exists. But it's not always the case that that something with one-sided limits will have a two-sided limit. Good, okay. Here's a very interesting result that we can use to compute certain limits. So this is called the squeeze theorem, and I'll show you a picture to illustrate these words on the next slide. But the idea is, if you want to compute a limit for some difficult function g that you don't really know how to bound or describe very well, but luckily you have these two other functions lying around, f and h, and they have the property that g is always lower bounded by f and upper bounded by h, possibly equal. So if you have that structure where f is less than or equal to g is less than or equal to h, and that holds for all x in some interval around the point you're interested in, and you happen to know the limits for the lower bound and the upper bound, so you know the limit as x goes to a of f is L, and you know the limit as x goes to a of h is also L, then you know that the limit as x approaches a of the inside function g must be L, because g is somehow being trapped between h above and f below, and both f and h approach the same value L. So g has nowhere else to go. I'm not going to prove this because I'm going to ask you to actually write out the proof of this theorem in the second consolidation document. So we'll just assume that it's true and use it to compute an interesting limit. But first the picture. So
Oh boy, look at those squiggly.
it's so squiggly and colorful. But yeah, let's suppose g is this weird oscillating function. It jumps around and it's hard to study explicitly. But we have, again, another function h, which bounds it above, and f, which bounds it below. And h and f come and touch, and they have this limiting value of L at a. Then as you can see, g gets squeezed between them, and it must also have the same limit. The limit as x approaches a of g of x equals L. Okay, is that intuitively clear?
Yes.
Okay. It's actually kind of a bitch to prove, even though it's very clear, but I will scaffold it for you. But again, okay, so we're not proving it, we're assuming it's true, and now we're just going to use it. All right.
Well, it seems easy to prove because if the limit as h of x approaches a, if those two are equal, then the only possibility, because of the equal signs in the inequality signs, quotation marks,
This thing?
it's a possibility that really works there.
Yeah, but that's just an intuitive argument, right? To prove it, you actually need to say let epsilon greater than 0 be given, and you have to tell me how to get a delta that makes g with that makes the absolute value of g minus L less than that epsilon, right? So this is one of those results that the picture makes it seem like it should be very easy, and it seems almost obvious. But to actually prove it, you have to tell me how to get the right delta, right? So there's some playing around where you have to use the deltas for f and h to construct a delta for the g, right? Good. Other thoughts or questions or comments on squeeze theorem?
No.
Okay. Let's study this new function that you may not have seen. Well, it's built out of functions you've seen, but this is called the Sinc function, not to be confused with the hyperbolic sign. That was cinch with an H. This is Sinc with a C. And electrical engineers use this a lot because it has a nice Fourier transform, and electrical engineers just have massive boners for signal analysis and Fourier transforms. But anyway, so the Sinc function, Sinc of x, is sine x divided by x. So if you don't like the name Sinc, you can just call it sine x over x. That's the definition. And we're going to prove that the limit as x goes to 0 of Sinc, which is sine x over x, equals 1. Now you can see that this is not totally obvious, because if you think about this as kind of, the limit should be something which is for nice functions related to what you get by plugging in the value there. We can't plug in 0 because 1 over 0 is undefined. And we also can't really think about just, dividing the top by the bottom because sine of 0 is also 0. So this thing naively looks like it's going like 0 over 0, which doesn't give us any data about it. So staring at the fraction doesn't help us very much. And using epsilons and deltas is a bit harder because we don't really know how to bound these components very nicely. But as we'll see, we can actually prove that the limit exists and equals 1 using the squeeze theorem. So let me go back to the previous slide quick. So the whole punchline of the squeeze theorem is we need to pick an upper bounding function h and a lower bounding function f and try to squeeze the value of here sine x over x between those two. So I'll ask you for an idea. What do you think we could use for the top one, the upper bounding function?
Could you reiterate the question?
So what should we choose for the upper bounding function? I think I called it h. So we want to find a function which is greater than sine x over x, but has the same limit that it approaches 1 at 0. So can you think of a function which is always greater than or equal to sine x over x near 0, but it also approaches 1 at 0?
I believe you can use cosine here.
Cosine. Is cosine always bigger than sine x over x?
Yeah.
No, I don't. Yeah, cosine. Let's see. Near 0, cosine is 1. Yeah, I think cosine's going to be smaller than this. But I think we could just use the constant function 1, right? Because sine x is a y-coordinate of a point on the unit circle, so sine x is going to be upper bounded by 1. And I think near 0, sine x divided by x is also going to be upper bounded by 1. We should show that a little more carefully. But I think the upper bounding function we can use is just the constant, h of x equals 1. Bad h. Let me show a graph, though. It might make this a little more intuitive. So, good. Okay. So the line's a little thin, but you see this middle black curve. That's the sinc function. So that's sine x over x. Then there's this green line here, which is which I'm going over in orange, but the curve is green. That green line is the constant line, just y equals 1. And cosine, in fact, will be our lower bound. So by looking at the graph, you could see that near 1, cosine is always going to be below the sinc function. We haven't proven that yet. I'm just giving intuition. But we want to upper bound with the constant 1 and lower bound with cosine. Good. Questions on this? Or do you believe me? Okay. Now we have to do the proof, though. We have to actually prove that 1 upper bounds and cosine lower bounds. Okay. To do that, we're going to use this interesting trick to find this bound. It's related to when we prove the law of sines by computing areas and using that, setting those equal. So I've drawn a triangle and a circular arc and then another triangle. We're going to compute those 3 areas. So the first triangle goes from the origin O to this point P on the unit circle. So the green is the unit circle. So there's a point P on the unit circle determined by the angle theta down here. And then it comes down to the point 0, 1, which is Q. Q is 0, 1. So first let me ask you, if we're finding this area of the orange triangle, which is a half base times height, and the base is 1 because this thing goes from O to Q, we need the height. So what is the y-coordinate of the point P in terms of theta, using some trigonometry?
Sine of theta.
Good. So then the area should be what altogether? So the height is sine theta, and we...
Right.
Yeah.
This would be... Oh boy. Half of sine of theta.
Yeah, just half sine theta. Good. Remember, the goal here is to bound sine theta, show that it's between cosine and 1, or sine theta over theta, I guess. Good. Okay, so now there's this extra area here, which I'm shading, which is part of the circular arc, but not part of this triangle, right? So we want the area of this whole pizza slice now that includes the triangle and also this extra wedge piece. And we can compute that just by remembering that the area of a circular wedge is just a fraction of the total area in a circle. So the total area of this circle is pi. The angle is theta. And then how many radians are in a total circle?
3 pi. Excuse me, 2 pi. I don't know how I messed that up.
2 pi. Okay. So good. If the total area is pi, and we have a slice which is theta much of the whole 2 pi, then what is the area of this circular arc?
I believe that this is... Thinking intensifies. Theta divided by pi.
Let's see, it's pi times theta over 2 pi, right?
I just simplified the thing up there. What I had in my mind before that was pi divided by theta.
Pi divided by theta. No. This should
Right
be
either.
should be theta over 2, right?
What?
Right, because it's
Oh my god.
2 pi times theta, or sorry, 2 pi, what am I doing? Pi is the total area, so the total area is pi. The fraction we have is theta over 2 pi, and the pi's cancel, so it's theta over 2. Good. Okay, so this whole thing's theta over 2. Now there's a blue triangle, and this part's actually kind of interesting. So there's a way to figure out what this height is. What is the height of the blue triangle? And the way to see that is just to use our trick that that for any triangle, not necessarily one on the unit circle, for any right triangle, the sides are related by sine, cosine, and tangent. So tangent of this angle theta is opposite over adjacent for the blue triangle. But adjacent is 1, because this side length on the bottom is simply 1. So that means tan theta is simply the height of the blue triangle, which means this height is tan theta. Is that step okay, or is that too fast?
Say it again.
So if we just look at the side lengths of this blue triangle, let me just emphasize which one the blue triangle is. So this bottom length is 1, and this height, I don't know, for now you can call it x or something. We're trying to solve for x. So x is that height we're interested in. And then if you just took opposite over adjacent using theta in the bottom left, that pink theta, theta is an angle of the blue triangle, so tangent of theta is the ratio of the opposite side to the adjacent side. The opposite side is this x we're trying to solve for, the height. The adjacent side is simply 1, since that down here is a 1, so I put x over 1. But that's just the statement that x, the thing that we're trying to find, the height, is exactly the same as tan theta. Right. So I have to skip this.
Okay. Makes sense.
Okay, good. Yeah, it's a little, it's kind of backwards, because normally you know, I don't know, you know the height and you're trying to find something about theta, but here we're just determining the height. But anyway, okay, so then what's the area of this guy? Since now we have the same base is 1, the height is tan theta, so what's this area?
Tan theta divided by 2, or tan theta, half of tan theta, I don't know, however you want to work.
Half tan theta looks good. Okay. All right, now for the magic. Just kind of looking at the picture, geometrically you could see that the orange area is less than the kind of green area of the sector, the whole sector, which is in turn less than the area of the blue triangle. So we have, I guess, less than or equal to in principle, but we have a chain of inequalities between these three. So they all have a half, so I'm just going to get rid of the factors of a half. But the statement then is that the smallest one is sine theta, right? So sine theta is less than theta, which is less than tangent theta. Okay. And now we want to get a bound on sine theta over theta, right? That's the thing that we're interested in. So if all of these things are positive, then I think we can invert, right? So if, for instance, since if 1/3 is less than 1/2, then when you raise both sides to the -1 power to flip the numerator and denominator, you have to reverse the sign or the direction of the equal sign as well, right? The inequality. 3 is greater than 2. Have you seen this in algebra when you flip the inequality sign flips as well?
I have seen the inequality as multiplying by negatives, but not this.
Yeah, when you either multiply by negatives or invert, right? If you flip the numerator and denominator. I mean, we certainly believe that it's true, because if we didn't reverse the inequality sign, then we would say 3 is less than 2, right? That's a bit of a problem. Okay, so let's invert all of these. 1 over sine theta is less than 1 over... Oh, I didn't. Said I was going to do it, and then I didn't. It's greater than 1 over theta is greater than 1 over tan theta. Okay. Okay, so we're trying to... Let's see. Did I just get myself confused? What are we trying to do again? We're trying to want to show that cosine of theta is less than sine theta over theta, which is less than 1. Let's just think about the first piece with the cosine and the sine. So how do I do that? I think what we want to do is multiply across these, right? So we're trying to get an expression in terms of sine theta over theta. So yeah, I think that's right. Okay, so we need to just manipulate these two inequalities we have. So this is what we want to prove. We have sine theta less than theta is less than tan theta, and 1 over tan theta is less than 1 over theta is less than 1 over sine theta. So then I think if we multiply through, going to get, we multiply through by sine in this inequality, right? So I'm just going to multiply all three pieces by sine theta. So sine theta times 1 over tangent. Well, what's that? Tangent is sine over cosine. So let me do this on the side. So sine theta over tan theta. What does this simplify to? I don't know if you could do that in your head.
Well, this would be sine theta divided by tan theta, or sine theta times, I believe, cosine over sine.
Yeah, so sine theta times cosine over sine, and then the sines cancel, and we're left with what? Or was that too fast?
Theta.
What'd you say?
Cos theta, cosine theta.
Yeah, cos theta, good. Okay, so when I multiply the leftmost thing by sine theta, I get cosine theta. When I multiply the middle guy, 1 over theta, by sine theta, I get sine theta over theta. When I multiply the right guy, 1 over sine theta times sine theta is 1. So in going from this step to this step, I just multiplied everybody by sine theta. Okay, so now we're effectively done. So we know, well, we haven't proven this, but cosine of theta has the usual property that its limit as you go to 0 is simply the value you get by plugging in. So if I plug in, I get cosine of 0, which is 1. So this thing has the limit of 1 as theta goes to 0. The right side, well, that's just a constant function, so the limit of a constant function as we go to 0 is also 1. And therefore sine theta over theta is squeezed between those two limits. So it's just like as we claimed in the image down here, that sine theta, or I guess I switched from x to theta, but sine x over x gets trapped between the constant value 1 above and the cosine below, and therefore its limiting value is also 1. Good. Is that clear? Do you buy that argument?
Yes.
Okay. I've swept one subtlety under the rug, which is that the proof that we did with the triangles only had positive values of theta, so for it to work, we really also have to think about the negative thetas, but it's the same argument. It just goes through. I'm not going to repeat because it would be the same words, but with just negative values of theta. But good. Okay. I kind of like this question because I mean this thing about the three triangles. It's I think a very cute geometric argument to get something which is really just a statement about limits. Okay. Any other thoughts or questions on this before the interlude?
I have no thoughts or questions on this. I like it.
Good. I like this one too. Okay. Let's see. We're 45 minutes in. Good. I think I'm doing all right on time. So here's the kind of big picture of really what the rest of the book is about in one way of looking at it. So you could think of what we're doing in calculus as giving us a new language to talk about nice properties that functions could have. And you could imagine kind of the study of calculus as ranking functions from least nice to most nice. So by not nice, I mean something which behaves strangely or counterintuitively. Like remember that function which was 1 on the rationals and 0 on the irrationals, right? That's not a very nice function. It doesn't behave the way that you would expect. And indeed, it's kind of even below the last line on this scale, because that function did not have a limit which exists at any point.
It gets no love.
Yeah, it gets zero affection from me. It's nice as a counterexample, so I mean, I like it in that sense, but it's I don't know. It's not
You're
well.
just so easy to hate.
Yeah, pathological functions are, I don't know, they're like villains. So the first criterion of niceness that we could impose is saying the function has to have a limit which exists at every point. That's like the baseline for niceness. As we saw, Stars Over Babylon has this property, that the limit exists at every point, even though it's very jumpy. The next step of niceness you could impose is say, now the function has to be continuous, which I'll define for you in a moment. But this is basically just the statement that the limit exists and it's actually equal to the value of the function at that point. Right? So this is something like a function which has a hole and then there's a different value. Like this would not be continuous even though the limit exists at that point, right? The question of whether the limit exists doesn't care about what happens at the point, but the question of continuity does. Continuity says this is not continuous because even though the limit exists, it's not equal to what you get by plugging into the function at that point. So this is even nicer. Up the scale next is integrability. All integrable... Oh, sorry. Actually, yeah, I think these two should be switched. Yeah, why did I do that? These two should be switched, I'm sorry. Every continuous function is integrable, but not every integral function is continuous. I have these backwards. When we study integrals, this is the question of finding areas under curves. So every function which is continuous has the property that you can define an area under it, but there are some functions that you can't define an area under them, like that function that's 0 and 1 on the rationals and irrationals. It doesn't make sense to speak about an area under that function. Then getting even smoother is differentiable. This means the function has a derivative, which we'll study in chapter 3. So again, as you go up the scale, you have all of the properties below. So every differentiable function is integrable, every differentiable function is continuous, and every differentiable function has a limit at every point. And you can ask that it has more derivatives. So you could say, not only does your function have a derivative, but its derivative has a derivative. That's called C2, twice continuously differentiable. Or you could repeat that n times. Say the function's derivative has a derivative n times. That's this thing called Cn, where you can insist that it has infinitely many derivatives, smoother and smoother and smoother. So that's C infinity, infinitely many times smoothly differentiable. But the king, the absolute nicest functions in the entire world, are called analytic functions. And you know that analysts like something when you take the name of the subject, mathematical analysis, and you give a class of functions a name that sounds like analysis. They're analytic. And these functions are quite remarkable. The definition is that an analytic function can be written as some convergent infinite series with powers. So in some sense, analytic functions are like, I guess n equals 0 to infinity. These are like polynomials with infinitely many terms. I mean, ordinary polynomials are also analytic because you could just say, well, most of my ANs are 0 except the first 2 or something. That gives you a line, for instance. But remarkably, the nice thing about analytic functions is that they are so tightly constrained that if you give me the values of an analytic function on any interval, no matter how small, even if it's the interval from 0 to 10 to the minus 7 or something, a very small interval, and you say these are the values of the function on that interval. In general, if you ask me to guess the function after that, it would be hopeless. I would say, how could I possibly tell what that function is doing at x equals 100? I only know what's going on this very small interval. So in general, the question is hopeless. If you tell me the function is analytic, and here are its values on that very small interval, then I would say, done. I know exactly what the function is. There's only one possibility, and you could just write it down. You could write down the value of the function on the entire line, knowing only its behavior on this very small interval, just by knowing it's analytic. It's called analytic continuation. If you know it on a very small interval, you can continue it uniquely. There's only one way to do it, to the whole line. Quite remarkable. So, just to, I guess, pace ourselves, we're studying these things now in chapter 2. Derivatives will be in chapter 3. I think integrals are in chapter 5. And then we'll study these analytic functions with infinite series, I think later, like chapter 7 or 8. But you can kind of think of calculus as our attempt to classify and study all functions by listing their properties. And it's kind of a strange result that even though that question about how do we understand these functions by discussing their properties, it sounds very abstract. There's no a priori motivation about applying it to the real world or anything. But mathematics is very generous, and it rewards you for asking seemingly abstract or unapplicable questions, because as we'll see, as we answer each of these, it will turn out almost by magic that the object that we have defined in order to understand that property of the function is going to be remarkably applicable to all sorts of real-world scenarios. Derivatives tell us about position, velocity, and acceleration, and from there all of classical mechanics and all of physics. Integrals will allow us to compute the way that a changing quantity accumulates, so that you know, for instance, if there's a leaky faucet and the speed at which water comes out of the faucet changes over time, you can find the total amount of water that's leaked out over any interval you like. And, I mean, really, it's impossible to list all the applications, because literally every field of science and engineering uses these as kind of like the basic language. So that's the big picture roadmap. We're constructing our scale of niceness of functions, and along the way we'll find that every step of niceness has beautiful connections to real-world applications. Thoughts on this?
I'm looking forward to learning.
Sorry, maybe this is a little boring, and I should just say what the actual stuff is. But
Wait, what?
I thought you were being sarcastic. Or were you serious?
No.
Ah, good.
I'm actually looking forward to this, trust me.
Okay. I don't know, the way you said it made me think you were eye-rolling or something, but okay, good. I'm happy. Alright, with that motivation, let's do the first, well, we already have the first step. Let's do the second step of continuity, which should really be the third step because I wrote them out of order.
Actually, I think that my brother just arrived.
Ah, okay. We can stop now then and do continuity when you return from Scotland if you like.
Or tomorrow, I don't know. I don't think I have anything going on.
Okay, yeah, tomorrow works for me, really, anytime.
Yeah.
Good, okay. Enjoy your visiting. Thanks for your attention.